Good day, folks. This is tutorial number 34 in the playlist that is Dynamic Scenario in 3D Experiences platform. It's a simple problem that is handled in a vibrations course, elementary vibrations course, and it deals with what is called rotating unbalance. So suppose you have a propeller that's turning, but there's a chip in it, or a washing machine or a dryer that the load is unevenly distributed in the compartment. What happens? You will hear vibration taking place, significant vibration taking place, and that's because there is an object that's rotating, and that object does not have a full symmetry or balance. Okay, it's called a rotating unbalance. Now, in a vibrations class, something like that is handled as a single degree of freedom system. That's a simplified analytical model. So we have this mass here, extra mass, unbalanced mass that's rotating at an angular velocity here, omega, and it's an offset. There's an offset between the axis of rotation and the position of the mass. Okay, and then we have a whole machine, could be the weight of the washer and dryer, or the mass of the washer and dryer, etc., which is called M, and it's mounted on springs and dampers because of the internals of the machine. Now, the displacement of the mass, the displacement of the big mass as a function of time from the static equilibrium position. In other words, before you start the machine, this thing sags down, for example, at a particular location. That's what we call equilibrium position, static equilibrium position. And the x that we're going to get is measured from that level. Okay. And this m includes is the total mass, which includes m naught. So actually, if you look at this block here, the mass of the block is essentially m minus m naught, but when you add the whole thing up, you're going to get m as the whole mass plus the unbalance. You're shown in a course like that the x of t can be measured. X of t can be measured from this equation. And here, big X is the amplitude of the vibration from the equilibrium, static equilibrium position, big X. And the theta is the phase difference between where the mass is, where the m is, and basically where m naught is. But we're not interested really in theta. We're interested in this big X, at least when I do this problem for you in 3D experience. And the force transmitted to the ground is calculated through this. Now, in these expressions, the R is the frequency ratio, and what that means is that the ratio of the frequency in radians of rotation of this mass over the natural frequency of the system. Natural frequency of the system is root of k over m. Okay, so let's move on. I did a MathCAD sheet for you so you can see what is it that we're going to be calculating from the experience and what do we have to compare it with. Now, this is the magnitude of x, depending on the data that I've given here, 1 kilogram mass of that unbalanced piece, 20 mass of the whole thing. 720 is stiffness of the spring. Eccentricity is 0.05. And the damping coefficient is 20. Okay, the natural frequency. The frequency of rotation is going to be 5. It is 5 given to you now. This I should have called this thing omega r, where I left it as omega, and that means the period of oscillation, steady state oscillation of this object is 1.257. So once you have this data, you can find the damping ratio. Here's the natural frequency. And notice that 5 is relatively close to 6. Okay, so we expect pseudo, if you want, resonance, large displacement, etc. But anyway, if you plug these things into the expression for x, we're going to get the displacement of the mass. That rectangular block should be around 5 millimeters, and this is the amplitude of the vibration. Okay, and the transmitted force is sinusoidal with the amplitude of 3.76 Newton. So these are the things that we're going to be comparing it with. Now, here's the way I'm going to model this thing. So we have a frame, we have a block, I have a rod and a mass, and when these are all assembled on top of each other, you get something like that. And this green arm or the rod is going to be turning at the given speed. Now, notice that what I have done, in order to make sure that I'm dealing with the static equilibrium position, I make sure that when I specify the reference length of this spring, okay, when I use the reference length of the spring, I use zero point 0.1 because these are model dimensions are going to be given to you, but what I'm saying is that for the reference length, I use where the block is located before the motor starts. And I'm going to use 5 rad per second as indicated in the MathCAD worksheet. And these are dimensions in case you want to do that yourself. These dimensions are irrelevant. The only thing that's important is that really 0.1 in a sense, and that eccentricity. This eccentricity is very important right there. 0.05. Okay. Now, what I do is I put the you have to define the mass of the frame and the mass of the rod in spite of the fact that we are assuming that the mass of the frame does not participate in the motion, and the rod, I'm going to assume it's massless. So I put a very small mass on the rod, and the mass of the frame, it really doesn't matter what it is, but you need something because you're doing dynamic scenario. Now, for the block, I'm going to use 20 kilogram, and for the uh, unbalanced mass, I'll use 1 kilogram. So let's go ahead and do that. Now, I have already created these things, so I'm not going to bother making it again. It's right there. Let's go and create our mechanism and then put the stuff on it. First of all, I want to assemble this thing. Let me move to assembly design. Okay. Now, I'm going to anchor the base. So let me go ahead and anchor the frame, fix the frame. That's fixed. You can see that. Then I'm going to create my, for example, place this thing in the frame, make a prismatic joint here. So we go prismatic. The different templates that we use, we really don't care. So I'll use this one. Yeah. So I use this edge and that edge. Okay. This plane and that plane. Okay. And I don't need to control the motion of this thing. So this offset here, I'm going to delete it because I'm not controlling the prismatic joint. All right. Now the only thing is that I want to make sure that the distance from there to there is 0.1 meters. Now, in order to do that, there are different ways of achieving it. I'm not even sure what it is right now, but let's go ahead to this prismatic, not prismatic, but to engineering connection, and there's an offset here, and I'm going to say the offset between this plane and that plane, create a new connection. I want it to be 0.1, and it is. If this was not 0.1, I want it to be 0.1, then you change it here and you say, okay, so it's in the right spot. And then I don't need this thing. I don't need this. I'm going to delete it. It's created a planar joint, but I don't want it. I'm going to delete it. The only reason that it created that planar joint is that I wanted to make sure that this distance is 0.1. But anyway, it's gone. Now we're going to do the revolute. So here, let's go and do a revolute. What is that? Revolute. Axis to axis, plane to plane. I use this template. Okay. Click on it. Win. I use the axis of this hole. Okay, that's fine. And the axis of this pin. All right. And I use the plane, this plane of this block and say the plane of this, the back plane of that. Doesn't matter. Okay. And because I'm going to put a motor there, I have to control this angle. So I'm going to use a vertical plane of the rod. So vertical plane of the rod, that'll be, which plane would that be? Let's check. For example, XZ plane of the rod, XZ plane of the rod, and this side plane. It really doesn't matter, or XZ plane of the block. Either way, XZ plane of the block. I think it's this. Yep. Let's make sure. Yep. I'm going to control that. Right now it's 90 degrees, which is fine. And then we're going to rigidly attach this to that. Okay. So first thing, I'm going to move it to that location. So I say snap, snap, smart move, snap. Okay. This to that, and which is already done. We can see that. And we're going to do, actually, I don't think, yeah, okay. And then snap, that face to this face. We may have to move it because I don't think it's in the right spot. Okay, so let's clear it up now. One more time, snap this axis. I want the axis of, you see, I don't want that thing. I want the axis. How about making, let's see now, what's the best way of doing this thing? Okay, so the best way of doing this is perhaps this and that. Let's see. Yeah, is that the right spot? Okay, so I'm not sure. Let me see that. You see? Yeah, looks good. Okay. So they're snapped in position. The thing is that with the snapping, no joints different. Let me create a rigid joint. I will use this template. So it's going to be between the mass and the arm. Okay, that's good. So I created a rigid joint. Good, we're almost done here. So we're pretty much done. Actually, let's go to mechanical systems design, apply masses. So if you go all the way to the right, here's the weight definition. Everything is red because nothing has been defined. You go to the frame and then click on this hyperlink and make it out of steel. And it really doesn't matter because it's not going to be moving. Go to the block, click on this hyperlink, make it out of steel, and then change it to be 20 kilogram, right? Yep. Okay. Click on the rod, click on the link, make it out of steel, and make it extremely small, for example, 0.0001. Pretty much massless, you can see. And good. And close it. And finally go to the mass M0, click on the link, make it out of steel, and change it to be 1 kilogram. 1. Done. So we have defined the properties that we want. Okay, very good. Let's create our spring here. Here is the axial spring, and the axial spring goes between this point, which is at the bottom, at the very bottom, at the center of that bottom rectangle, and the one that is over here. Now, let me see. I don't see it there. So let me go ahead and go to my frame, and I created a point there. Let me see now. Which point would that be? That'll be probably this. Yeah, right there. See that? This point and that point. Click on the f of x. Put 720 there. That was the stiffness of the spring. Okay. Click on the damping. F of x. Put 20 there. That was the value of the damping coefficient. And click on the reference length and put 0.1. Even if you don't put 0.1, when I say OK, when you say OK, it's going to take that distance. But it is fine. Very good. So we have done these things. Just create our mechanism representation. Click on the mechanism manager. And what you see is that you have a fixed part, prismatic, revolute, rigid, and spring. Good. Now, say okay. Let's make sure that our revolute does have constraint. You're right there. Very good. Okay. We're pretty much done here. So now we're going to go to the mechanical systems experience. Say okay. Say okay. First of all, let's do an excitation, motor excitation. So you click on the velocity motor excitation. Give it time. This pops up. It says, where is your motor? The motor is at revolute. And notice that if I had on the command, if I did not have that command for that revolute, I will not be able to pick it. But I did put a command there, you put it there, and I put the, was it 5? I think it was 5, yeah, 5. 5 rad per second. Let's make sure that is correct. Yeah, 5 rad per second. And then we say, okay, good. And let's put a sensor somewhere. The different things we can do. I noticed that what I want to do is to find it. One of the things that I want to do is to find the uh, the distance between the end of the end of this block, this point, and that height. Now, I forgot to do something which I'm going to do right now. Uh, I'm sorry. I will go back to my frame. I go back to my frame. In the frame, I will make a plane. I'll make a plane, and the plane that I'm going to make is essentially going at that height, right? So there are different ways of doing it. One way is to say, okay, offset plane, offset from a plane, from this plane, I offset it to be 0.1. Set all the way at the bottom of that orange piece, right there. We can see that. Good, good. So we go back to our excitation or mechanism, actually. Here, you go back to your mechanical systems experience. And now we're going to put first of all, a, uh, let's see now, measure the distance between this plane and that point. Okay, that's one thing that I did. And then I'm going to put a joint force probe. You click on it. You select if you expand this thing, you select the spring and give me the force at the frame down here. We say okay. That's pretty much it. So let's go and create our dynamic scenario. Motor, as an excitation, we send to the right hand side. Probe, these both go to the right hand side. Okay. And while I'm at it, let me also do a probe at this point, for example. Let me go and do a position speed and acceleration probe, for example, at this point, or it doesn't matter, the point at the bottom of the point at the bottom of the it makes no difference at the bottom of this orange piece, but this point will do, any point. So okay, and make sure you include it. Yeah, it's already included. Now, as far as the duration is concerned, I click on that tab, we put down, sure, 10 seconds, and 0.01 is fine. We say fine. The cell is the integrator that we're going to be using, and let's go ahead and run it. Let's go ahead and run this thing for 10 seconds. First, we're going to measure the distance between that point and the plane, and that better be the amplitude of the vibration. So click on view scenario results. Deselect everything. The very last item, this length is going to give you that uh, amplitude. And notice that this is a steady state. Initially, of course, when the motor starts, there's transient stuff, and then we look at it, it's 5 point something, 5 point maybe it's yeah 5 point something 10 to the minus 3, and that agrees with what we have here right there, almost 5.2 10 to the minus 3. Okay, the period is 1.257, and that you can actually see it. If you look at these distances, it's going to be around 1.2 something. Okay, now let's go and look at the force. So click on specification. Don't show me this, show me the force in the z direction. And notice that here's the steady state, and you have roughly 3 point something, 3.89, 3.9 Newton, and that's something in this along this line. I mean, you can look at the values more closely. Don't eyeball it. You can go where is that? You can go here and say table, and the values are given, and go and look at exactly what that amplitude is. And that's pretty much it. So we did a good job here. Everything matches, and that's it. Good luck.